Welcome back to Boiler Wild. My name is Eric Johnson. As you hopefully know by now, I am your one and only host. This is me by myself today. Hopefully, we're going to drop some knowledge on you that you didn't know, make you better, and make you more informed in the boiler room. Some quick housekeeping items. I wanted to read a note or message I got from Anthony in Maine. This podcast is awesome. I started late in my profession at 40 years old and have now been in for 7 years. There's so much to learn. I have so many disciplines. One of my favorite codes in Maine is that it is the duty of engineers to teach other boiler operators. Thank you so much. I've been looking for something like this since I started. So I appreciate notes like that. I appreciate any and all communication. Hate mail, you can just throw away in the trash. I don't appreciate hate mail, but I love all the positive notes. I've gotten a couple now that people have sent me either on email or LinkedIn. We can also send it on Facebook. I'm on Facebook as well and Instagram, but mostly email and LinkedIn. Boiler Wild, you may be wondering how it got its name. The WILD is an acronym, stands for work hard, invest in yourself, lead others, and develop yourself into a person of excellence. That's where the name comes from. And today on episode 34, we're going to be talking about boilers and battery and lead lag sequencing. A very, very important topic to understand, as well as being able to know how to set up boilers. So let's start with first things first is boilers and battery. What does that mean? And by battery, that's battery, spelled the same thing as like when a battery in a car, same spelling, but it's a little different. And if you Google it, Google doesn't have a great definition for it because it thinks you want a boiler battery or electric boilers, and that's not what we're talking about here. So boilers in battery is two or more boilers connected to a common steam header that allow them to operate together and share a common steam supply. So when you have just one boiler and you have a load, you don't even really need a steam header. You just pipe out of the boiler and you run the steam wherever it needs to go. When you have more than one boiler, so now we have two boilers, now we need a steam header, and the steam essentially is generated and collects in the header for distribution. All the boilers will produce steam. The steam exits the boilers, it enters the header, and then gets distributed to the loads and via the piping off the header. And this is assuming that the boilers all feed together into the same steam system. I don't think I've ever seen a system where boilers are next to each other and they don't feed together into the same steam system. I don't know why somebody would do that. If you needed different pressures, you would just use a reducing station. So I don't know. Maybe there is a scenario where having boilers close together but not connected to have different steam supplies would be or something, but I can't think of it. So anyways, boilers and battery, and this could be any amount of boilers. You could have 10 boilers, and that's 10 boilers and battery. And this is with steam boilers. I don't know if technically hot water boilers, if it's technically boilers and battery, but I'm going to go with it's just for steam boilers. The name was made for steam boilers when steam was very prevalent and hot water boilers were not so common. In order to have boilers and battery, we have to have a way to isolate the boiler from the rest of the boilers. And there's different codes and laws about this. and it varies state by state, but ASME will have different things to say about it. And it depends if you're a low pressure or high pressure boiler. But typically, when you have multiple boilers and battery for steam, for a high pressure boiler, you will have, and high pressure is anything over 15 psi, you will have a non-return valve and you will have a stop valve or an isolation valve on your header right after your boiler. So you have your steam exit coming off your boiler, you have your non-return, and then you have your stop valve. A non-return valve is essentially like a check valve. It has a movable seat inside of the valve. When steam is flowing out of the boiler into the steam header, that movable seat will be open. But when steam is not flowing out of the boiler into the steam header, that movable seat is supposed to close and keep header pressure from flowing backwards into the boiler. Now, how well does that actually work? Well, non-returns are, I've never seen one last more than 6 months that it doesn't bleed pressure back into the boiler. They will hold when they're brand new, but you get a little operation on them and they'll leak by. And they seem to be more trouble than what they're worth. I understand what the operation of them is and what the intended purpose is, but having a non-return, you have to almost constantly change them in order to keep their desired operation the same. And a seat moving and restricting most of the steam flow can be better than restricting no steam flow. So that's a thing, but a non-return valve is different than a isolation valve. An isolation valve is just going to be a manual open close of the seat. And when it's open, basically the steam doesn't see the valve at all. There's nothing there to stop steam flow from either side of the valve. It could go both directions across the valve. I'll also note, I forgot to mention this, that non-return valves are only required on boilers that have a manway in them. So you'll see some smaller boilers that don't have a manway access, and a non-return is not required. Like I said before, there's different requirements for different jurisdictions and different requirements for ASME Section 1, which is power boilers, high pressure steam boilers, and then Section 4, which is low pressure steam boilers, anything 15 psi or down. So look at those requirements if you need more specifics, but we're just talking more general right now. Where I've seen issues before is, we are in the age of customers want everything automated, and we have all these burner controls and level controls and all the DA and feed water controls and firing rate controls and plant lead lag controls that automate the whole steam system, except for some parts of the water treatment. The biggest problem I've seen, though, with lead lag with steam boilers is bringing on a boiler that is cold or the steam pressure is different than the rest of the system. In a perfect world, let's say we have 4 boilers in battery. We're running at 100 psi, and we only need 2 boilers to keep the load right now. So these 2 boilers are running, and then the main plant lead lag system brings on a 3rd boiler and says, hey, we need more capacity. We're going to bring on a 3rd boiler. This 3rd boiler, you have to slowly warm up. It's probably not going to be warm. However, since the header valve is open and the non-return is open, even though the seat will be slid closed, it's probably likely that the non-return leaks pass and the boiler will be at or near 100 psi. even though the water is warm to, coldish. It's not going to be whatever 100 psi steam temperature is, 300 degrees or whatever it is. And you can have issues, especially if you run your lead lag system only off of pressure, where it will just bring on the boiler and I'll see that the boiler has close to 100 psi on it, and it will think that the boiler is ready to go full fire, where in reality you need to warm up the boiler, and you have all these thermal shock concerns. And there are controllers that have thermal shock warm up with water temperature, which is recommended versus steam pressure for the reason that I just mentioned. Is you cannot rely on steam pressure in an off boiler to be an indicator of how warm the water is and how ready the boiler is to make steam. If the non-return held at 100%, the steam pressure in the boiler would be at 0 or close to 0. And the lead lag system would see that the boiler is close to 0 pressure, and it would slowly warm up the boiler. And the boiler, steam and pressure flows from high to low. So the boiler would not be able to produce steam pressure, until it got above the operating pressure of the plant, which in this example is 100 psi. So as we're warming up the boiler would be, say, at 20 psi of steam. All that steam is going to be maintained inside of the boiler. We're not going to be able to flow out past the non-return, as on the other side of the non-return, we have 100 psi. But the non-return is keeping that 100 psi from flowing backwards back into the steam boiler. However, what actually happens is that 100 psi will leak back into the boiler. The boiler is at or near 100 psi. The third boiler is brought on automatically by the header pressure. And if you don't have cold start, it thinks that boiler is ready to go and produce steam. In reality, the burner has to fire and warm up all that water. And that delay causes the lead lag system to think that it still doesn't have enough boiler fired, and it may bring on the fourth boiler, and the fourth boiler will have the same problem, and it will be cold, and then eventually what will happen is it overshoots. There are ways to avoid this. However, from an automatic standpoint, steam plants are not as automatic as customers want them to be. When they have all these automatic controls, bringing on a new boiler, it can be problematic, especially when the non-return is sold as a check valve to keep pressure out of the boiler and to keep a boiler from filling up with condensate from steam flowing back into a boiler that's off. So let me cover what happens there. A boiler will be off, and if you have a leaky non-return or even no non-return, steam is going to flow back into that boiler. Even though it's off, steam is going to flow anywhere it can because it's a gas. And when the steam gets in the boiler, it is not going to look around and be like, oh, I'm in the wrong spot, let me flow out of this. No, steam is going to take up the space in the boiler. And as you cool steam, as you know, the steam will turn to condensate, and that will raise the water level of the boiler. And the water level will eventually get high enough where it'll trip your high water level alarms, or it just won't. If you don't have a high level water alarm, the water will just keep filling and filling. And sometimes, when you fire the boiler, you can get away with a high water level. But sometimes if you leave a boiler off long enough, the water level will fill up the entire steam space of the boiler. And now when you fire the boiler, you can have water hammer and water entering your header due to the fact that you have no steam space in the boiler. And that can cause a dangerous scenario, especially if the boiler doesn't warm up slowly, and that requires a lot of manual operation. Now, there are ways to get around high water. I know some vertical boilers have, I am familiar with Fulton vertical boilers. Their VMP system, they have this on their website. They have a full engineering document. It's, a couple pages, and they address this lead lag issue of steam boilers, and they designed into the boiler design to have a high water steam trap. And if the water level inside of the boiler in these vertical boilers gets above the outlet or inlet for the high water level, the steam trap will allow the water to exit the boiler and go back to the feed water or DA tank. And therefore, it will naturally allow the water level to stay pretty normal inside of the boiler, and you are not wasting water and heated water and steam to drain if you are constantly blowing down a boiler or dumping a boiler in order to keep it out of high water level. These vertical boilers that this Fulton system that Fulton has designed, and I'm sure other vertical boilers have the same design, is they also don't have a manway, so they do not need a non-return. And since they do not need a non-return, all the boilers stay at the same pressure and stay heated, and therefore theoretically can bring on a new boiler. Fulton also advertises that on the VMP that you can just take a boiler from 0 to 100% firing rate, as the boiler is entirely symmetrical and there's no risk of thermal shock. And that's why having a boiler warmed by the steam and have the water level controlled by the steam or the high water trap outlet that feeds the water back to the feed water tank or DA tank. And then the steam keeps the water semi-warm, but then if the boiler is needed, the burner can come on and just fire right at 100% and produce steam pretty quickly. And this allows for less energy waste, and obviously it allows for reduced costs. Now you don't need a non-return for each boiler. This keeps the pressure across all the boilers the same. And, there's benefits to it. Now, some people don't like a vertical boiler. Sometimes you can have issues with contractors piping the overflow trap to drain. You will waste a lot of water, heated water, a lot of water treatment chemical when you pipe it to drain. That can be an issue. But the whole point is to try to solve the problem with having boilers and battery and having non-returns leak, and boilers are cold even though they have the system pressure on it. And that's just one design Fulton has for their vertical boilers and how they design them to work together. Other manufacturers have similar designs or different ways to go about it. What I've always wondered is, why don't we have automatic valves for steam headers? And I'm pretty sure it's just a cost thing, as an automatic 8-inch valve that's rated for steam pressure probably can be pretty expensive. And by automatic, I mean opened by a electronic actuator. How I would see that working, and I don't know if there's any ASME codes against this, but how I would see that working is an automatic valve would either be connected to the main plant lead lag system or the boiler, or both. And the valve would close. You would essentially be closing your stop valve every time the boiler is off for more than a set period of time. So if the boiler is off for more than 30 minutes, 45 minutes, we would close this stop valve, and it would allow the boiler to cool down, and it would also keep steam pressure from entering back into the boiler through the non-return valve. The valve would have to be a slow open, slow close valve. You could put an actuator on it that takes 3 minutes to open. There could be some scenarios I see where you'd have to be pretty specific with the coding and how it works. But I think an actuator with a 3-minute timer to open, go from full close to full open, would allow enough time for the valve to even out the pressure. You also would have pressure on the other side of the valve, so you wouldn't have a huge differential. And this would, I believe, make a battery of steam boilers more automatic and keep the water levels easier to manage than having just a stop valve and a normal stop valve and a non-return. There's probably a reason why this isn't done. I know there's some boilers out there. You can put a pressure reducing valve backwards on it, and you can keep pressure inside of the boiler. So when it's backwards, the valve will only open once the boiler exceeds a certain amount of pressure, which keeps a set amount of steam pressure on the boiler, which can help keep the water level calm and to kind of even out steam demand. I don't think that will stop 100% of pressure coming back. So I think that's a little different scenario and problems of why we would use a pressure reducing valve on a individual boiler. But I've always wondered about the automatic stop valve, and it's probably mostly due to cost. Like I said, I haven't seen anything from ASME on it. There's probably an issue with opening up a header automatically, but I don't see how that would be much different than some other things that happen automatically. I know a lot of jurisdictions, and I don't remember what ASME talks about, automatic blowdown, automatic bottom blowdown. Like companies would ideally want automatic bottom blowdown, and I've seen it done once, and I don't think ASME has anything about it. I would have to check, and I'm sure different state jurisdictions have it. But in order to be a fully automatic system, the blowdown, like there's no reason why we couldn't have automatic blowdown. Now, the downside of that is, if one of the valves gets stuck open or leaks or the piping breaks, now you're dumping an entire boiler that's hot pretty quickly, which can be a serious safety issue, with an operator not there. But there's also a lot of benefits. Now if something breaks, an operator isn't standing right there where all the hot water and steam is. The water's going to come out and instantly flash the steam. And I think it also provides a little bit of responsibility. If you make boilers too automatic, even with operator rules, companies get lazy, people get lazy, and they don't watch them. And the boiler in itself can't really tell if it's building up scale, if it's corroding its tubes, if there's issues with it, if gaskets are leaking on the fire side or water side, and an operator, stationary engineer, somebody is around to watch it, to check on the boiler. It's always important. So for bottom blowdown, automatic valves have a ton of benefits. They would also keep water treatment and build up a sediment in the bottom of the boiler. Like an automatic bottom blowdown would always blow down the boiler at 7 a.m. every single day. You wouldn't have to rely on an operator to remember to blow it down or forget, and now you fill a boiler with scale and a bunch of mud and sediment. But that's kind of a tangent for boilers and battery. Let's talk about lead lag. So for lead lag for a steam system, we can have two ways of controlling a boiler. We can have parallel or sequential. Parallel is, if we have 4 boilers, parallel would be boiler 1 fires to 10%. Then we bring on boiler 2 and it fires to 10%. Then we bring on boiler 3 and it fires to 10%. Then we bring on boiler 4 and it fires to 10%. And all these settings can vary, but now all 4 boilers are firing and they will all modulate the same. So boiler 1, 2, 3, and 4, they'll modulate up to 15%. They'll modulate up to 20%. They'll modulate up to 30%. Oh, we now have less demand for steam. Our boilers will all modulate down to 15%. And if we get below a certain threshold, say all of our boilers are firing below 15% for 5 minutes, the lead lag system can get programmed to drop off the 4th boiler and go to 3 boilers. And now all 3 boilers are going to move up to 22% to maintain the steam pressure instead of having 4 boilers at 15%, whatever it is. Every lead lag system, you can move the ons and offs, but that's what parallel is. All the boiler firing rates move up and down in parallel relatively. You can set like the first boiler to come on and not call for a boiler till it gets to 50%, but it will then split that between 2 boilers. So instead of one firing at 50%, they'll bring on a second boiler and now 2 will be firing at 25%, and they'll modulate up and down. And once 2 boilers get to 50% again, now we can bring on a 3rd boiler. But as you can see, the boilers are firing the same firing rate. Sequential firing is boiler 1 fires from 0 to 80% or 100, but depending on the situation, 0 to 80%, and then brings on another boiler. And boiler 1 is almost like the lead, and then boiler 2 is going to fire to 40%. Boiler 1 is going to go to 100%. Boiler 1 keeps going up to 80%. And then now we're going to bring on boiler 3, and it's going to fire up to 40%, 50%, fires up to 80%. Now we bring on boiler 4. And all this while, boiler 1's firing at 100%, boiler 2's firing at 100%, boiler 3 is firing at 80%, boiler 4 is firing at 40%. Sequential is the lead boiler, and it's not always boiler 1, but I'm using boiler 1 as the lead boiler in this example. Boiler 1 will fire at 100%, and then the load will taper off from there. So if the load requires 2 boilers at 100% and a boiler at 50% and a boiler at 20%, boiler 1 is going to be 100, boiler 2 is going to be 100, boiler 3 is going to be 50%, boiler 4 is going to be 20%. It is sequential firing rate, and if the load drops off, boiler 4 will shut down, then boiler 3 will shut down, boiler 2 will shut down, but the firing rate will not be even. Boiler 1 firing rate will always be the highest, and the last boiler, in this case, if all 4 are firing boiler 4, the last boiler 4, will always be the lowest firing rate. And that is sequential. It is in my experience that sequential is recommended for steam operation, as the more efficient steam boiler is going to be the one less boilers firing at a higher percentage. As you bring on steam boilers, they get less efficient the more you bring on. You end up using your baseline of energy increases. You have all the gas usage or fuel usage, whatever you're using. You also have the electrical energy. And on a larger boiler, you can have a 500 horsepower boiler, the electric motor, the fan size, that takes a significant amount of energy to turn that fan and produce all that combustion air. This is opposite of hot water boilers, and specifically condensing boilers. Condensing boilers, the parallel or sequential firing is parallel is recommended. If you have 4 boilers that are hot water condensing boilers, you want to bring on as many boilers as you can at the lowest firing rate that you can. And that is going to reduce your stack temperatures, which increases your efficiency of the boilers, which will raise the efficiency of your entire heating plant. So you want to bring on as many boilers as you can in parallel at the lowest firing rate that you can, which increases the efficiency. This is different than steam boilers, as I said. It's 2 different ways of controlling what's right or wrong. There's no right or wrong. It's just theory. If you do find a steam system where you find that parallel operation works better, you can set your lead lag system run parallel. However, it is just recommended that a steam system is going to run in sequential. And then if you have a hot water operation with condensing boilers, you can run the boilers in parallel and run as many as you can at the lowest firing rate as possible, which can be different than what most people will think. I've had previous customers and experiences where they think the more boilers are on, the more energy that's being used. But you have to look at total energy of the plant. And when a boiler is at a higher firing rate and it's a condensing boiler, the amount of heat going up the stack will increase at the higher firing rate. It gets less efficient the harder the boiler fires, the more heat input it has. For hot water non-condensing boilers, would still recommend parallel. You're still going to have a increase in efficiency if the boilers are running at a lower firing rate, which is going to be a lower stack temperature. The biggest way to make sure that you are running efficient, if you have a primary variable system, is to make sure your isolation valves are working. If you have boilers that are off but have water flowing through them, you'll have a natural draft going through the boiler, and you will be losing heat up the stack. And the boiler is essentially, instead of adding heat to the system, it's removing heat to the system, but it's unnecessary. You're wasting heat up the stack. And that's why ASHRAE 90.1 mandates that for all the hot water boilers, if the boiler is off, it doesn't have any flow in it. For a primary, secondary system, a pump is required to flow water through the boiler. So you just shut the pump off and that will stop flow. And with check valves, you should have very minimal flow through the boiler when the pump is off. So let's do a quick recap. Boilers and battery, 2 or more boilers connected to a common steam header, allowing them to operate together and share a common steam supply. Boilers and battery, most often, especially with high pressure steam, will require if the boilers have a manway, will require a stop valve and a non-return valve. However, non-return valves are notorious for leaking, and there will be tons of issues like I previously described. Make sure your lead lag system, if you are bringing on boilers that have thermal shock issues, make sure you are slowly warming up boilers. Your lead lag system should have the capability to do that. Make sure you're warming up a steam boiler, preferably off of water temperature, not off of pressure. Then parallel and sequential firing rate. Sequential is recommended for steam. Parallel is recommended for hot water. You don't want water flowing through a boiler that's off, so either you need to shut off the pump or shut off the isolation valve. With primary variable, you will have to keep one isolation valve open, otherwise on your lead boiler. Otherwise, you will shut off all flow to the system, and you don't have to have boilers on in order for the load to be taking heat out of the water, but you have to have somewhere for the water to flow. And a primary variable system, all the water flows through the boilers. And if you shut off all the boiler valves, now you don't have any way to flow water unless you have a bypass. And I have seen some manufacturers talk about that. Instead of leaving the lead boiler open on the valve, they would shut that and open a bypass. But I haven't seen that as a common thing. And until ASHRAE says something like that, it's probably not going to be common. But hope you learned something at around 40 minutes. So that's a good stop for today. Easy stuff to learn. Hopefully you understand parallel and sequential firing rate. Just another tool of knowledge to add to your toolbox to make you better in the boiler room. If you've gotten this far, I appreciate you listening. You can do me a solid by rating the podcast 5 stars if you learned something, if you like the podcast. If you have any questions or any topics for me to cover, you can email me, eric.johnson@boilerin.com, or you can DM me on LinkedIn. Both of those are great. Thank you for listening, and stay wild.